Dear students, I would like to continue with the theory of probability, and today I would like to tell you something about random vectors. So, till today, we worked with random variables, so-called random numbers, and random vector is in fact the vector of random variables. Officially, it is the vector on some probability space, and then the elementary events are some concrete combinations of random numbers which can occur. But we can imagine this as the vector of random numbers. And in this course, we will continue two cases. We will consider, I'm sorry. The first case is that we observe let's say n marks, I would call it marks or properties on one randomly chosen object. And the second one we observe mark or property on an object. And so, some examples. When we observe n marks or properties, or we can call it by many other names, on one object, it can be, for example, the situation when you come to the bank, you ask for a credit in a bank, and then the bank asks you some questions and try some signs. So it can be, for example, what is the sex of the client, what is the salary of the client, what is the education, and so on. Yeah? So then, when we denote sex as a random variable x1, which can be either 1 for males and 2 for females, salary, which is a random number x2, and then the salary is some okay. Let's say in euros, okay? And so some k euros for k, in fact, from real numbers, but usually we consider the whole euros. And so k euros is the salary of the client. Education x3, which can be, for example, 1 for primary school, 2 for secondary, school or high school, and 3 for university education, and so on. And so then, when a randomly chosen client, when some random client come to the bank asks him the questions, what is your sex, what is your salary, and so on. And we have probability, or we'll work with probability later. And then we have the realization x1 is equal to 1, x2 is equal to 2000, x3 is equal to 3. For the first client, x1 is equal to 2, x2 is equal to 1000, x3 is equal to 2. For the second client, and so on. And what we are interested in is the probability of the behavior of x1, x2, and x3 together. It is called joint distribution, meaning that we are interested in the probabilities of the combinations of values for all these random variables. And we are also interested in some relationships among the random variables which form the vector. And so that's the aim in the first case. In the second case, just briefly, we can be interested in the heights of 30 children in the first class of a primary school. And then we suppose that these heights are independent. Because in the first class, we have the children from many families which are not connected. So therefore, we suppose that these heights are independent in the sense that one height has no influence to another height. And then we are not interested in the relationship among the random variables in the vector, but we are interested in some characteristics. And so, for example, we have the first height 130 centimeters, the second child is 135 centimeters tall, and so on. And the last children is I don't know, 127 centimeters tall. And then we are interested not in the relationship among the random variables, but we are interested on the behavior of each of the random variable. And because we suppose that it is the same sign, the same mark, the same property, we suppose that this property, this random variable, is the same for all these n objects. So here we study the behavior of xi while we suppose that xi that all xi have the same distribution. And it is the topic for statistics. So it is the topic which we start later in few weeks, next week or in 2 weeks. And so for now, we are interested in the first case when we observe some properties, some signs on a randomly chosen object, and we are studying these joint probabilities and relationship among the random variables. So, when we study the distribution, it can be described similarly as in the case of random variable by so-called cumulative distribution function. And in the case of random vector, the distribution function is the function of n variables, x1, x2, and so on till xn, where the description, the formula for the definition of the distribution function is that it is the probability that the first random variable in the vector is less or equal to the first variable, the second one is less or equal to the second variable, and so on till the nth random variable is less or equal to variable xn. So it can be briefly written in the form of the intersection of all these situations. And of course, it is defined for all xi from minus infinity to plus infinity. In fact, this distribution function can again describe the behavior of the random variable completely, but it is not very useful to work with it. So it has the same or analogous property to the properties of distribution function of random variable, but I would skip this case, and I would focus on the discrete and continuous random vectors separately. So what does it mean that the random vector is discrete? It means that each of its parts, each of the elements, so it means the random variable in the vector is discrete random variable. So it means that each random variable in the vector can take only finite or countably infinite number of values. And since we have some finite number of variables in the vector, it means that also the number of all combinations of the values in the vector is either finite or countably infinite. And it means that each combination can be given a concrete probability so that the sum of the probabilities is equal to 1. How can it look like? Let's consider an example. We have a discrete random vector where I will denote its variables not x1, x2, x3, but x, y, and z. Yeah? So just a short remark. We will denote the random vector x, y, z instead of x1, x2, x3. And because it can be a little bit confusing with the indices, so I will use the variables without these indices. And we suppose that x can be 0, y can be 0, z can be 0 with probability 1/4. The probability that x is equal to 0, y is equal to 1, z is equal to 0 is 1/4. Probability that x is equal to 0, y is equal to 1, z is equal to 1 is 1/8. The probability that x is equal to 1, y is equal to 0, z is equal to 0 is 1/8. And let's say probability that x is equal to 1, y is equal to 1, and z is equal to 2 is 1/4. No other combinations occur. So we have only these 5 combinations in the random vector. In order, it is easier and it is faster to calculate. Now, When we are interested in the behavior of these combinations, we are given the concrete probabilities, but we can be interested in the random variables separately. So we know the distribution of the vector, the joint distribution of the vector, and we ask what is the behavior of its parts of, let's say, the random variable x. The behavior of the separate parts is called marginal distribution. And when we care about the marginal distribution of a concrete random variable, the approach is the following. We look which values can be taken by x. And we can see from these combinations that x can take only 0 or 1. So the distribution of x is the distribution of the probability 1 between two values 0 and 1. So the probability that x is equal to 0 can be calculated from the joint distribution, but maybe you want to calculate it as, okay, there are 3 situations when x is equal to 0, so the probability is 3 over 5. But we know that the probabilities of the situations, of the combinations where x is equal to 0 are not equal. So the probability that x is equal to 0 must be calculated as the sum of the first, the second, and the third probability, because x is equal to 0 in these 3 cases, which occur with the given probabilities. So the probability is 1/4 plus 1/4 plus 1 over 8, which is 5 over 8. And the probability of x being equal to 1 is, of course, 1 minus 5 over 8. So it must be 3 over 8. Or we can calculate it as the sum of the probabilities of the combinations where x is equal to 1. So 1 over 8 plus 1 over 4, which is, as we expected, 3 over 8. Okay? So, in fact, it means that x has Bernoulli or alternative distribution with the parameter 3 over 8, because the parameter is equal to the probability of x being equal to 1. But it's not important whether you write it in this form or in the shorter form. And similarly, we can calculate the marginal distribution of y. Y can be similar as x equal to 0 or 1, and the probability that x is equal to 0 is equal to the probability of the first case plus the probability of the fourth case. So it is 1 over 4 plus 1 over 8, which is 3 over 8. And then the probability that y is equal to 1 must be 5 over 8, 1/4 plus 1/8 plus 1/4 is really equal to 5 over 8. So again, we can write it in shorter form. Y has alternative distribution with the parameter 5 over 8. Okay, and what about Z? Z can take 3 different values, 0, 1, or 2. So it is none of our known distributions. It is a completely general discrete distribution. And the probabilities are again given by the sum of the first, second, and the fourth probability for x being equal to z. So it is 1 over 4 plus 1 over 4 plus 1 over 8. So it is 5 over 8. X is equal to 1 with probability 1 over 8, and it is equal to 2 with the probability 1/4. Yeah, that's it. Questions? No questions? This is the marginal distribution of the items of the random vector or of the separate random variables in the vector. But we can study also the marginal distribution of some subvector. So for example, marginal distribution of the subvector xy is the distribution of the vector xy independently on z, or not independently, of course, it must depend through this joint distribution, but we care only about the values, the combination of values for x and y. So it means that we care about the probability that both these variables are equal to 0. X is equal to 0, y is equal to 1. X is equal to 1, y is equal to 0, and both these variables are equal to 1. And the probabilities of the combinations are again given by the table. So we have, by the joint distribution, I'm sorry. So we have only one combination 0, 0 in the joint distribution. It is the first one. So the probability of 2 zeros is equal to 1/4. The probability that x is equal to 0 and y is equal to 1 is the sum of these two probabilities. So it is 1/4 plus 1/8. So it is 3 over 8. The probability of the third combination is directly from the joint distribution 1 over 8, and the probability of 2 ones is 1/4. The sum of all these probabilities must be again equal to 1. It is, so it's done. Yeah? So this is the way how to find the marginal distribution of the separate random variables in the random vector, or of some subvector of the random vector, depending on what we care of. Yeah? So what does it mean practically? Practically, it means that maybe the bank is interesting how many men and women, I mean, what is the ratio of men and women among its clients, or what is the distribution of the education among the clients, and so on. And then the bank decide not to study, let's say, the education, but only the sex and the salary. The salary can be high or low. So the practical meaning is that we are not interested in some parts, and we're interested only in some smaller parts of the random vector. And in the continuous case, it is very similar. So in the continuous case, it means that all the random variables in the random vector are continuous random variables, and then the vector must be described by so-called joint density. And the joint density is the continuous function of n variables. It is difficult to write it or to draw it. So we will do sometimes some easy example on the exercise. But you must imagine this situation as the density being given by continuous function of n variables, n-dimensional function. And again, the probability that the first item is lies between A and B, the second item lies between C and D, and so on, is described by the integral. Now, I mean n-dimensional integral from A to B, from C to D, from this density. Yeah, so the way of calculation with the density is the same. And of course, when we derive the marginal distribution, we use our typical approach. The sum is replaced by the integral. The probability is replaced by the density. So it means that when we want to derive the density of the ith item, of the ith random variable, the approach is using the integral instead of the sum, using the density where the ith item, the ith variable is fixed. It is the variable of the density we are deriving, and the integral is n-1 dimensional, because the ith item is fixed. It is the variable of the density here. So it is the analogy to the situation when we calculate the probability that x is equal to 0. X is equal to 0 was fixed, and we calculate the sum of all probabilities where x was fixed to 0 and the other variables were changing. So this is the analogy to this situation. Okay, and now when we have a random vector and we can work with marginal distributions, we can derive the characteristics of random vector. Now, okay, I'll start here. So, when we studied random variables, we calculated usually two characteristics, the expected value and the variance. And we have some analogy to these characteristics in the case of random vectors. The expected value of a random vector is nothing than the vector of expected values of all random variables in the vector. So in our case, it means that the expected value of x is the vector consisting of expected value of the random variable x, expected value of the random variable y, and the expected value of the random variable z. Expected value of x is equal to 3 over 8. You can calculate it either as 0 times 5 over 8 plus 1 times 3 over 8, or you can use the information that x has alternative distribution with the parameter 3 over 8, and the parameter is equal to the expected value. Analogously, expected value of y is 5 over 8, and the expected value of z is equal to 0 times 5/8 plus 1 times 1/8 plus 2 times 1/4, which is 5/8. So it means that the vector of expected values is 3/8, 5/8, and 5/8. And this is the first characteristic of the random vector in our example. The second characteristic was the variance. And the variance was, in fact, the characteristic describing how wild the random variable is, meaning what is the mean square jump of the random variable from its expected value. It will be also considered in this case, but in this case, because we have the vector consisting of many random variables, and we are interested in their mutual relationship, we will include this variance to a more complicated structure called variance matrix, or sometimes it is called covariance matrix. So this is the first characteristic, and the second characteristic we will study is the variance or sometimes called covariance matrix. Let me describe what covariance of two random variables is. It is defined as the expected value of the product of the difference of the first random variable from its expected value and the difference of the second random variable from its expected value. So, imagine a situation. Now, it is not the case of our example, it is another example where U is education and V is the salary class. The education is 1. I mean, U takes the value 1 in the case of primary school, 2 in the case of secondary, or high school, and U is equal to 3 if the client or the randomly chosen person studied at the university. Let's consider 4 salary classes first. So V is equal to 1 if the person is has the lowest salary, and so on. V is equal to 4 for the highest salary. And here we have rather lower and rather higher class, not important. important is that the salary and the educations are ordered. Imagine that, for example, or let's suppose that the expected value of U is 2.1. And so it means that many people have secondary schools, quite large percents of people has university. So let's suppose that the expected value of U is equal to 2.1. And let's suppose that the expected value of V is equal to 2.3. Now, what happens in the situation that we consider the product U minus the expected value of U times V minus the expected value of V? For a person from primary school, it means that his or her education has the value 1. But the expected value, meaning the mean value, is 2.1. So the education of this person minus the mean education is negative. We suppose that the person from primary school does some work which is not paid very well. So we suppose that the salary of such a person is rather lower. So it means that he belongs to the first or to the second class. And when he or she belongs to the first or second class, it means that his salary class minus the mean salary class is negative. Negative number times negative number is positive number. Now, consider a person from a university. The education of such a person is equal to 3. And 3 is higher than 2.1, than the mean value. So it means that the education of such a person minus the mean education is positive. And we suppose that the person from university is a manager of some project or some developer, programmer, I don't know what. It is a person which rather belongs to the higher salary classes, either to the class 3 or to the class 4. So it means that the class minus the mean value of the classes is positive. And positive number times positive number is positive. So in the most situations, it happens that this product is positive. So it means that in average, in the mean value, this product is positive. And this is the covariance of U and V. So when we order the education from the lowest to the highest and the salary class from the lowest to the highest, we can see some independence that lower education means rather lower salary and so on. So it means that these two random variables, these two random numbers cooperate in the sense that when one of these numbers is growing, then the second one is growing as well. And when first of them is decreasing, then the second one is decreasing as well. And so they cooperate in this direct sense, yeah, that they behave in the same sense, in the sense of growing or decreasing, increasing or decreasing. And what happened in the situation that let's say we ordered the salary class in the opposite direction. So it means that the highest salary is the first class. Then rather higher salary is second class, and so on and so on. The lowest salary is the fourth salary class. Let's suppose that the expected value is 2.7 now. And again, study what happens for the person from primary school and from university. So for a person from primary school, again, it's his or her education is 1 minus 2.1, which is negative. And if this person is doing some badly paid job in the company, his salary belongs to lowest or to the lower salary classes. So it means that the number of his or her salary class is 4 or 3, means that 4 or 3 minus 2.7 is positive. Negative number times the positive number gives us a negative number. When we consider a person from the university, the education minus the mean education is positive for such a person, and the salary class for such a person is again sum from the higher salary classes. So the number of class it is first class or the second class, the number of class minus the mean number, mean order of class is negative. So the product is negative. And again, we are in the situation that when we take a person from primary school or university, we get in the most cases the situation that this product is negative. When one number is higher than its expected value, then the second number is lower than its expected value, and opposite. So it means that this product is, in the most cases, equal to a negative number, so the mean is negative. It means that the covariance is negative, and it again means that these two random numbers, these two random variables, are dependent in some sense. We will talk about independence later, yeah, but they have the influence to each other, in the sense that if one of the numbers is increasing, then the second one is decreasing, and opposite. Yeah? So negative covariance means that the numbers cooperate, but it goes against to each other. Great. So when we want to calculate the covariance, which is defined as the expected value of this product, we can use an easier relation that it is expected value of the product of u times v minus the product of their expected value. The approach is an easy homework for you. You only do some operations with random variables and expected values we know about. So, what does it mean? It means that when we want to calculate the covariance in our case, in our example, we already have the expected value of x and the expected value of y. So the only missing thing is the expected value of the product x times y. And the expected value of x times y is again the expected value of a new random variable which is given by the product of these two random variables. As I said at the beginning, when we started with random variables, I said that also the sums and the differences, the products, and so on of random variables are again random variables. So what happens in the product of x and y? We take all combinations of x and y, calculate their product, and multiply their product by their probabilities. And then we make the sum of all these subjects. So it means that x and y can be either 0 and 0, or 0 and 1, or 1 and 0, or 1 and 1. And we want to calculate their product. The product 0 times 0 occurs with probability equal to the probability of the combination 0, 0. So with the probability 1/4. The combination 0, 1 occurs with probability 3/8. The combination 1, 0 occurs with the probability 1/8, and 1 times 1 must be multiplied by the probability 1/4. We can see that all members are equal to 0 except the last one, so the expected value of this product is 1/4. And it means that we can calculate the covariance of x and y. It is 1/4 minus the expected value of x, 3/8, times the expected value of y, which is 5/8. So it is 1/4, or I will write, okay. Okay, I will write it in this form. So it is 1/64. Yep. So this is the covariance of x and y. And as I said, the characteristic is the covariance matrix. So in the covariance matrix, when we have the elements or the random variables x1, x2, xn, on the position ij is the covariance between the ith item and the jth item. So it means between the ith random variable and the jth random variable. So in the covariance matrix, we want to construct there will be nine elements. Covariances of X, Y, and Z with X, Y, and Z. And first covariance which we calculated was the covariance of X and Y. So 1 over 64 is here. Now, we can see that from the definition or from the relationship for calculation of the covariance, we can see that there is the symmetry. So the covariance of X and Y must be equal to the covariance of Y and X. So it means that this matrix is symmetric and the covariance of X and Y is equal to the covariance of Y and X. Now, what about the diagonal? On the diagonal, we should have the covariance of X and X, the covariance of Y, and so on. So, for example, covariance of X and X is defined as the expected value of X minus its mean value times X minus its mean value. But this is nothing than the expected value of square distance of X minus its mean value, and this is what we call the variance of X. So on the diagonal of this variance or covariance matrix, we have the variances of the random variables from the vector. So in our case, since we know that expected X comes from alternative distribution with the parameter 3 over 8, the variance is 3 over 8 times 5 over 8. It is the variance of Bernoulli or alternative distribution. So it is 15 over 64. Analogously, covariance of Y and Y is equal to the variance of Y, which is 5 over 8 times 3 over 8, which follows from the fact that Y is also the Bernoulli or alternative distribution with the parameter 5 over 8. And the variance of Z is, because Z has none of our known distributions, we must calculate the variance from the relation expected value of Z square minus the square of expected value. And the expected value of Z square, I recall, is 0 square times the probability of times the probability that x is equal to 0, that z is equal to 0, and now I don't remember the value. Okay, it was written here, I don't remember it. So it will be calculated in this way. Then the expected value of z is the third item of the vector of expected values, and you would have the variance. So it is again an easy homework, as well as to calculate the remaining covariances. So you can try to calculate the remaining parts of this covariance matrix, and I will go further in this lecture. So the covariance matrix or the variance matrix is quite nice because it shows us some basic properties of the behavior of the random vector, the basic relationship among the random variables in the vector, in the sense that when the covariances are positive, then we know that these two numbers are growing together. When the covariance is negative, we know that in this couple of random variables, one of the random grows and the second increase, the second one decreases, and so on and so on. But the values have no meaning. The only reasonable meaning is the diagonal, or has the diagonal, because on the diagonal we have the variances. So we have the information of how wild the random variable are. But outside the diagonal, the information is quite weak. So instead of this covariance, we sometimes, or very often, we use a so-called correlation matrix, where the correlation matrix is the matrix with the elements given by the correlations. And you probably heard this term. The correlations are the covariances which are normalized by the square root of the variances of the random variables whose correlation we calculate. What does it mean in our case? In our case, the correlation of x and y is equal to the covariance of x and y over the square root of the variance of x times the square root of the variance of y. The covariance of x and y is equal to 1 over 64. The variance of x is 15 over 64. The variance of y is 16 over 24 as well. So it means that the correlation in our case is 1 over 64 over 15 over 64, so 1 over 15. And again, we will write these correlations to the matrix given by 3 rows and 3 columns. And the correlation of x and y is 1 over 15, which is equal to the correlation of y and x. In the same way, you can calculate the correlation of x and z, the correlation of y and z. So these 4 numbers are for your homework. And what about the diagonal? On the diagonal, we have the covariance of x and x over the square root of variance of x times the square root of variance of x. And since the covariance of x and x is, as we can see here, equal to the variance of x, the square root times the square root of the same of the variance x is the variance x as well. The correlation of the number with of the random number with itself is always equal to 1. So always on the diagonal in the correlation matrix we have the number 1s. And so in the correlation matrix we have no information about the variance of the random variables in the random vector, but we have some numerical expression of the dependence of the remaining of the couples of different random variables. So while in the variance matrix we have the information on the diagonal, meaning what is the variance of the separate item of the random vector, in the correlation matrix we have the information outside the diagonal, where the information is how strongly dependent the numbers are. Why is it the measure of dependence? Because the correlation, it can be proved that the correlation is always between -1 and 1. This is the meaning of normalizing the covariance. And 1 or -1 respectively are considered to be the strongest dependence. Because what can be stronger than the dependence of the number with itself, isn't it? The correlation is equal to 1 also in the case that we have two random numbers where one random number is a linear combination of is a positive real number times x. So you can calculate that when we have a correlation of x and a times x, it is also equal to 1, but only for positive a. If a is negative, then the correlation of x and ax is equal to -1. But in fact, the absolute value equal to 1 for the correlation means that the dependence is linear, and the linear dependence is considered to be the strongest dependence. Then it is very difficult to say what does it mean that the correlation is equal to 0.7 or 0.5. So you need more experience to work with this correlation in order to feel the meaning. But the truth is that when the correlation is close to 1 or to -1, the random variables are very strongly dependent. The last thing which I forgot here is the notation of these matrices. When you open a book with covariance matrix and correlation matrix, you will find many notations. So maybe the most often notation is capital sigma of x, but it looks like the sum, so you can also use the variance with capital V or the covariance with capital C. And as I said, it's not unique in the literature. The same situation occurs with correlation matrix. Sometimes it is denoted as rho, sometimes it's correlation with capital C. Again, it is not unique, so you can choose from this notation when you calculate this matrix. I don't care. It's up to you. And when I see that you know what to calculate, you don't need to use some classical notation. So this was the topic of characteristics of random vector. And now, finally, we go to the term which I used very often, but I'm ashamed without a definition. And the term is the independence of random variables. So what does it mean that the random variables in the random vector are independent? So the definition looks quite terrible, but it is not so terrible when you remember what the independence of random events means. So let's call it A, B, C, and D, the random events. Are independent if and only if it holds that the probability of their intersection is equal to the product of their marginal probabilities, but it was not enough to verify this one relation, but we needed to verify these relations for all combinations we can obtain from these four events. And so for all triples, it must be satisfied as well, and also for all couples, it must be satisfied that the probability of the intersection of the events is equal to the product of their probabilities. So to all couples, it must be satisfied as well. And for random variables, we have the same description, but instead of the random events in the brackets, we must have some behavior of the random variable, because there must be some situation in the bracket. There must be some event, some process in the bracket. So for random variables x, y, z, u, it is analogous, but instead of A, we must have some behavior of X, and the general behavior which can be described is, for example, that X is less or equal to I, because it is satisfied for discrete random variables, continuous, or it can be described by the probability for discrete random variables, continuous random variables, their combinations, and so on. Yeah? So it means that x, y, z, and u are independent if and only if probability that x is less or equal to y, y is equal to j, z is less or equal to k, and u is less or equal to l, must be equal to the probability that x is less or equal to I times the probability that y is less or equal to j times the probability that z is less or equal to k times the probability that u is equal to L for all I, j, k, L from real numbers. But again, we must verify this for all combinations which can be made from these 4 random variables. Yeah? So it must be satisfied for all triples and all couples. And when we have n random variables, then we must verify this relationship for all combinations of all dimensions or all length which we can imagine. And this is the meaning of the definition of independent random variables, which is seen on this slide. Yeah? So the probability that the product of that the intersection of x less or equal, not important, than something must be equal to the product of probabilities that the item is less or equal to the same value, must be satisfied for all combinations which we can make from our n random variables. Yeah? This is the definition. But what is nice? It is nice that while the random events were quite arbitrary, but they described some concrete situation. For example, is the even that the number of spots on the die is odd, or the number of spots on the die is less or equal to 3. Then it is very concrete, and in the definition of random variables, we have this condition that I, j, k, and l are arbitrary real numbers. So it must be satisfied for all I, j, k, and l from R. So in fact, the behavior which we describe in the brackets is stronger. But, or not but, but what is nice, what it means for us, it means that then the definition can be weaker. The following theorem, which in fact is also the instruction how we can verify the independence of random variables in practice, this theorem says that for random variables, the dependence can be defined only by the first relationship. So it is very, very strong theorem saying that when we verify this independence from the first relation, it follows that the relation is satisfied for all combinations, and from all combinations, it follows that it is satisfied for all random variables. So this following theorem says that it is enough to verify the relation for all random variables in the vector, and we obtain the independence. So that's nice. And how we work in practice? Imagine the situation that we have only two random variables, x and y. Okay, x and y. And x can be, let's say, 1 and 2. Y can be 3 and 7. Not important. Their joint probabilities are 1/12, 1/6, 1/6, and wait. One half, 1/4, and 1/6. Yeah, now it should be okay. I hope. Yes. So, what does it mean? It means that in this table we have the joint probability. So, for example, this 1/12 is the probability that x is equal to 1 and y is equal to 3. And this 1/2 is the probability that x is equal to 2, y is equal to 7. And the question is, are x and y independent? So we must verify that probability that x is equal to 1, y is equal to 3 is equal to the probability that x is equal to 1 times the probability that y is equal to 3. Then the probability that x is equal to 1 and y is equal to 7 must be equal to the product of the marginal probabilities. And it must be verified for all combinations we can get. What are the marginal probabilities? What is the probability that x is equal to 1? The probability that x is equal to 1 is in fact the sum of these two probabilities. Because in these two situations, that x is equal to 1, y is equal to 3, x is equal to 1, y is equal to 7, we have the situation that x is equal to 1. So the marginal probability x is equal to 1 is the sum of these two probabilities, which are 1/12 plus 1/6 is 3/12, so it is 1/4. 3/4 is the probability that x is equal to 2. 1/3 is the probability that y is equal to 3. And 2/3 is the probability that y is equal to 7. And what we are in fact doing, the probability that x is equal to 1, y is equal to 3 is 1/12. The probability that x is equal to 1 is 1/4. And the probability that y is equal to 3 is 1/3. Is it satisfied? Yes, it is. Or does it hold? Yeah, it does. The probability that x is equal to 1 and y is equal to 7 is 1/6. Is it equal to the product of the marginal probabilities? The marginal probability x is equal to 1 is 1/4. And the probability that y is equal to 7 is 2/3. It is 2/12, so it is 1/6. Okay, it is satisfied. And so on. And what we are doing, in fact? In fact, we are looking at the number in the table and we check whether the number in the table is the product of the sum of corresponding row times the sum of the corresponding column. And so when we want to verify whether two variables are independent, we only need to verify for all fields in the table that the number in the field is equal to the product of the sum in the corresponding row and the sum in the corresponding column. In this case, 1/4 is equal to 3/4 times 1/3. And 1/2 is equal to 3/4 times 2/3. So, since we verified for all combinations of x and y that the joint probabilities are equal to the product of marginal probabilities, we can conclude that x and y are independent. Okay. And what about the situation that we have some other values in the table? One half, 0, 1/4, 1/4. RTs, x and y, independent. So again, we need the marginal distributions. 1/2, 1/2, 3 over 4, 1 over 4, and we start to verify. Is the probability that x is equal to 1, y is equal to 3, equal to the product of marginal probabilities probability that x is equal to 1 and y is equal to 3 is 1/2. Probability that x is equal to 1 is 1/2, and the probability that y is equal to 3 is 3 over 4. So it is 3 over 8. It is not satisfied. And since in the definition is that this relation must be satisfied for all combinations, then in the case that when we find at least one combination which doesn't satisfy this relation, it means that the variables are not independent. Yeah? So when we want to verify that they are independent, we must verify all combinations which we have. But when the conclusion should be that they are not independent, as it is in this case, it is enough to find one example when this relation is not satisfied, and then they cannot be independent. So if it is satisfied for all combinations, they are independent. If there exists at least one combination which doesn't satisfy the probability, the joint probability is not equal to the product of marginal probabilities, they are not independent. And similarly, we can verify the continuous case. We will do it at exercise. So I will skip it now. And I conclude this part by the theorem saying that when x and y are independent, then, of course, from the idea of the covariance, which is in fact the measure of dependence, the covariance must be equal to 0. But unfortunately, it doesn't hold on the opposite, in the opposite sense. So when the covariance is equal to 0, it doesn't mean that x and y are independent. So be careful. When x and y are independent, then the covariance is equal to 0. But it doesn't mean that when the covariance is equal to 0, x and y are independent. But we have one nice property. If you remember, what does it mean that phi implies C? And so one property implies another property. It means it is equivalent to the situation that the negation of psi implies negation of phi. And in our case, we know then x and y independent implies that covariance of x and y is equal to 0. So it means that when the covariance is not equal to 0, implies that x and y are not independent. And so what does it mean? It means that when we calculate the covariance, and we notice that the covariance is equal to 0, we have no information about the independence. But if the covariance is not equal to 0, we directly know that x and y are not independent. Yeah? So this is the relation between independence and the covariance of random variables. Okay, so that's all for today. And if something is not clear, we can solve it on the exercise. Thank you for your attention.